All right, everybody, welcome back. There's been some questions that have been asked that hopefully I'm going to address right now. The other class was experiencing some technical issues, and amazingly, I think we might have got them resolved. So if you have friends that have been avoiding the other class because of problems or whatever, tell them to give it a try, because I would like to get feedback to find out if our fix is actually working. With regards to your term exam, or let's talk about the labs first. Yes, you have a lab that is going this week, and you must complete the data collection by Thursday, tomorrow midnight. But that lab is not due for 2 more weeks because next week is reading break. And so nothing is going to be due reading break. You have no labs and no classes all of next week. And it is due when you come back Monday the 22nd rather than next Monday during reading break. Also, you have a term exam that is on Wednesday the 22nd, February the 22nd. The term exam will cover the kinetics chapter, which is chapter 20, and then chapters 15 and 16 out of the Equilibria module. The format for the term exam is not yet complete. Basically, my project over reading break is to prepare your term exam. And it is going to be a mixture of written response typed in, plus do calculations, and you'll be expected to do calculations literally on paper, and then scan and upload them to either the exam or to your TA. It depends on the technology that is available. William, you have a question?
Yeah, sorry, you said the 22nd, but a lot of us thought it was the 24th, the Wednesday.
I believe I said the 24th. I said that
But it is, just to confirm.
what I believe I said was that your lab quiz or your lab reports are due on the 22nd, the Monday, and your term exam was on the 24th.
Okay, perfect, thank you.
So that's your lab quiz, your lab report is due Monday the 22nd, and your term exam is on Wednesday the 24th. If I said 22nd, I apologize. And with regards to the material for that, like I said, chapter 20 and then chapters 15 and 16, the problem set 4 is available to you, and we're not gonna, part of it will be on the term exam, the part that deals with acid-base equilibria, which is what we are covering right now. Oh, the time of the exam? Right, good point. The exam will be 1 hour during the class window. So from 10:30 to 12:30, you will, whenever you start the exam, you will have 60 minutes to complete it. So you could start it at 10:30, 10:45, 11:30, but it will close at 12:30 for you. And so, yeah, so basically everyone's going to be writing overlapping time windows. Does that answer your question, Raphael? Good. All right. Are there any other questions before we start with the course material? Nope. All right. Well, then let us go and carry on with the course material. Last day, one of the last things that we did is we looked at the relationship between Ka and Kb for phosphoric acid. And these are the notes that, or the calculations that we came up with. We realized that there is a relationship, and of course deleting it does that, between Ka1 and Kb3, Ka2, Kb2. Basically, it's reverse reaction is the relationship. And when we go back and we were to look at the expressions here, we realize that Ka1 has phosphoric acid and dihydrogen phosphate. The only other place we're going to see those two entities is in Kb3, where you have dihydrogen phosphate and phosphoric acid as well. We already covered this, except we did not do the example associated with this question, and that was to determine the fluoride ion concentration, given the fluoride ion concentration in drinking water, determine the corresponding PF range. So that's what we are going to do now. And of course, we need to convert from ppm to moles per liter. So we have 1 ppm of fluoride, and that corresponds to 1 gram of fluoride in 10 to the 6th grams of water. That's basically what it means to be parts per million. And we now need to convert that to moles per liter. And I just lost everybody. Recording. All right, I'm back. So everyone can hear me, I hope. So 1 parts per million corresponds to 1 gram of fluoride over 10 to the 6 grams of water. And now we are going to multiply that and just convert it to moles per liter. Moles of fluoride per liter of solution. Looking specifically at the fluorine, we have 1 mole of fluorine is 19 grams of fluorine. And that converts from moles, or from grams to mole. With regards to the water, the density of water is approximately 1 gram per 1 milliliter. And then we have 1,000 milliliters per 1 liter of water. And so grams cancels, milliliters cancels, and I'm left with units of moles of fluoride per liter of water, which is exactly what I want. And when you do this calculation, you get 5.26 times 10 to the minus 5 moles per liter. And so the next step would simply be to take, negative, or the PF is negative log of the fluoride ion concentration, of course, which is that value over there, and that equals, what does that equal? Three, 4.28. My apologies. Don't have it written down somewhere. 4.28. All right. So that calculates the PF at 1 part per million. What is the fluoride ion concentration at 8 parts per million? And that is what I would like you to calculate right now, and plug the answer into the chat. $3.38. Other people get the same value? Good. So we get a PF value of 3.38. So that means that the pH or the PF range is 3.38 to 4.28. And that is what was asked for in the question. Did we, in this section, go over the significant figures associated with logarithmic operations? We did not? Oh. Okay. So that is the next thing I want to do. Give me a second so I can get to where I want to be. Oops. No, that's right. We have before. Yes. Okay, good. I thought we had in class. So, yeah, I'm not going to go in every chapter. It's the same rules of significant figures. The simple point that I want to remind you of is that we have the value 5.26 times 10 to the minus 5 moles per liter. The number of significant digits that are in this value is 2. How does that correspond to the PF value? Two digits after the decimal place. That is correct. So the number of significant figures in the value correspond to the digits after the decimal point. So this 9 is actually not significant, and it corresponds to the digits after the decimal place. The 4 out front corresponds to the order of the power to which it is raised, like where the decimal point is actually placed. Good. So, can you determine the pH of the following solutions without using a calculator? Can you do it in your head? Or just type it in? What is the pH of a 1 mole per liter solution? What is the pH of a 10 to the minus 14 mole per liter solution? Anyone? Or very quickly do it on a calculator? The pH of a 1 mole per liter solution is 0, yes. And for a 10 to the minus 14 mole per liter solution, it is 14. So given that information, what is the range of the pH scale? Zero to 14, okay. That is one answer. What I want to ask you is it possible to create a 10 mole per liter hydrochloric acid solution? Similarly, is it possible to create a 10 mole per liter sodium hydroxide solution? And of course, the answer is yes to both. So what is the pH of a 10 mole per liter hydrochloric acid solution? You give me the pH to that, and I will give you the pH to the 10 mole per liter sodium hydroxide solution. And we're getting lots of people typing in numbers. Yes, the pH here is -1, and the pH for the second one is 15. Because with the relationship H plus OH minus equals 10 to the minus 14, you're going to find out that the hydrogen ion concentration here is 1 times 10 to the minus 15, which gives you a pH of 15. Now, once you take activities into account, what you find that the absolute range of the pH scale goes from about -2 to +16. The common range that everyone talks about is 0 to 14, but with higher concentrations and activities, -2 to +16 is the absolute range of the pH scale. On the right-hand side is just a selection of common entities, chemicals, and the pH at which they exist. So the lead acid batteries in your vehicle have a pH of actually less than 0 because they're about 10 mole per liter sulfuric acid. Acid in your stomach is a pH of 1, but your body in general has a pH of about 7.3. That's the pH of blood. Notably, the acidic entities are generally foods, whereas the basic entities are generally cleaning products, whether it's cleaning and washing your hands or it's oven cleaner and drain cleaner, which are very, very high pHs. And we already did this, just as I jumped ahead last class to go through this, and we remembered that the 14 orders of magnitude is literally the distance from the Earth to the Sun when compared with a penny, which is 1.5 millimeters thick. Earth to the Sun is over 150 million kilometers. And the reason I was confused earlier was because of this slide that came up, and I thought we had done it in an earlier, and we had, and I already looked at that one on the tablet, so we're good there. That brings us to this. You now have the ability to calculate the Ka or pKa and B as required, given the limited amount of data that is present there. And so what I would like you to do is go through and calculate both the Ka and Kb values and pKa and pKb values that are unknown. I'm going to go over to the tablet and just write down those values so that we can fill them in. So as you put them into the chat, I will fill them in here. To the correct number of significant digits, s'il vous plaît. .04 is correct, yes. And if you need a reminder as to how this is set up and done, the relationships that you are using are Ka times Kb is Kw. And the relationship that applies for pKa values is pKa plus pKb is equal to 14, which is pKw. So what is the value for Ka2 and the remainder? You can do all of them. Benjamin says it is 2.0 times 10 to the minus 12. That is the value for Ka2. Good. Yeah, Ka2. Now you can do any one of the ones below, any number of ways. Anyone? Would it help if I reminded you that Ka1 and Kb2 are connected, and Ka2 and Kb1 are connected? pKb1 is 9.96, which you made the error and connected these two together, which isn't correct. It's pKa1 and pKb2, but that 9.96 goes there. But thank you, Ben. Much appreciated. $2.30 is the other one. Great. Thanks, Jason. How about the Kb values? Now you can just take the inverse log of the pK values, or you can take and compare it with the Ka values as well. There's more than one way of getting those. Last two. Kb1 is 5.0 times 10 to the minus 3 moles per liter. And the last one, one times 10 to the minus 1. I got 1.1. moles per liter. There we go. Now, the goal of that exercise was to calculate pKa's and Kb values, because ultimately you're only ever given the acid dissociation constants. If we go back to the table that we had previously, this one, here's a table of Ka values of monoprotic acids and pK and Ka values of polyprotic acids. You're never given the Kb values because you know how to go through and calculate them. And that's what this exercise did here. For the next example, we want to look at the autoionization of water. And of course, Kw is 1 times 10 to the minus 14 moles per liter at 298 Kelvin. Let's determine the pH of pure water at 25 degrees Celsius. We know the answer to this, but what we need to now realize is that Kw as an equilibrium constant is temperature dependent. And so Kw at body temperature, 37 degrees Celsius or 310 Kelvin, is 2.38 times 10 to the minus 14. And so we're going to determine also the pH of pure water at 37 degrees Celsius. So the reaction for the autoionization of water is simply that. And we have Kw is equal to 1.00 times 10 to the minus 14. And this happens to be at 298 Kelvin. To set up an ice table on our expression, not too concerned about water, but it's 0, 0, x, x, and x, and x. And just to go through my head, the equilibrium constant is much less than 1. I'm starting with reactants because I have to have some of this present, so all's good there. Now we can continue and look at our Kw expression. And if we plug numbers into that, we get 1.00 times 10 to the minus 14. Is equal to x squared. This gives us x is equal to 1.00 times 10 to the minus 7 by taking the square root. And just as a reminder, the hydrogen ion concentration is x. And so the pH is equal to 7. And again, that is at 298 Kelvin. That is the pH of pure water at 298 Kelvin. What I would like you to do is calculate the pH at 310 Kelvin, where Kw is 2.38 times 10 to the minus 14. What is the pH there? Go for it. To the correct number of significant digits. How many other people get 6.812? Excellent. And you are correct. 6.812 is the correct value. Good. Does anyone have any questions on those calculations? Good deal. All right, our next exercise is actually going to take us to the remainder of this class and into next day. By the time we are done this next example, we will have looked at all the possible pH calculations associated with simple acid-base equilibria, i.e. where there's only one equilibrium in solution. So we want to calculate the pH of a 0.35 mole per liter solution of a bunch of different acids and bases. And so basically what we're going to do is we're going to get started on this. The first one that is present is that of perchloric acid. Got the right color. Perchloric acid is on the list of strong acids, so it dissociates completely in solution. To give its ions. And I'm still going to use an ice table to follow the reaction. We start off with 0.35 moles per liter of perchloric acid, and initially 0 of those. Since this reaction goes to completion, we're going to lose 0.35 moles per liter of that. Gain, and this becomes that. Present directly in the ice table, because it goes to completion, is that the hydrogen ion concentration is 0.35 moles per liter, and so the pH is 0.46. And that's how the pH is calculated for a strong acid dissociation. The next thing that we're going to look at is that of benzoic acid. Benzoic acid is a weak acid, and we're going to go look at the Ka value in just a second. But this is an equilibrium and I'm just going to set up an ice table for right now. So I mentioned to you that it is a weak acid. If we go back and we look at our table of acids, just pointing this out, I mentioned this the other day, but I want to emphasize it, that this table is on the data sheet, and the data sheet is available to you on Blackboard. So you're able to go on to grab the data sheet, and you'll find under the acid dissociation constants, benzoic acid is listed with a Ka value, this is the top left-hand corner from fourth from the top, of 6.3 times 10 to the minus 5. And the appropriate units for that was moles per liter for that set of units. So the Ka value is 6.3 times 10 to the minus 5 moles per liter. This equilibrium constant is, of course, less than 1, so when we start with 0.35 moles per liter as reactants and 0 as products, we're actually starting on the side favored by the equilibrium constant. So the first step is done, and then we're going to lose some and gain on products. And we end up with that. The equilibrium constant expression, Ka, is that. When we substitute numbers in, we get 6.3 times 10 to the minus 5, and I'm just going to drop the units because it all works out, is equal to x squared over 0.35 minus x. Because the equilibrium constant is extremely small, we're going to make the assumption that this is x squared over 0.35. And the assumption that we're making is we're assuming that x is negligible in comparison to the initial value. With that assumption, we get x is equal to 4.70 times 10 to the minus 3 moles per liter. And that's just algebraic manipulation and taking the square root. We do need to check our assumption, and that is simply our x over our initial value, which is 4.70 times 10 to the minus 3 over 0.35, and that is 0.013. And that 0.013 is a little bit less than 0.05, but it is less than 5%, so our assumption is valid. So now our assumption is valid, and this is a legitimate value for x. We can go back up and see what we need, and we find out that x happens to be the hydrogen ion concentration. So x equals the hydrogen ion concentration, which is 4.70 times 10 to the minus 3 moles per liter. And so the pH is the negative log of that value, which is 2.33. Does anyone have any questions on that? All good? Well, I'm glad, Benjamin, because the mud's right now pretty darn frozen. So we're going to continue. And we're going to look at trichloroacetic acid as the next one. Trichloroacetic acid is CCl3COOH. And if you go back and look at the table, you'll find that there is a Ka value for trichloroacetic acid, and that is 3.0 times 10 to the minus 1 moles per liter. This is set up in exactly the same way as the other one. And we're left with that. Now the expression that we're working with is 0.30, 3 times 10 to the minus 1, is equal to x squared over 0.35 minus x. This value is not extreme. So it's very unlikely that you can make the approximation. It will not be valid. So you need to solve the complete expression, which is to say, when we do some substitutions, 0.30 onto 0.35 minus x is equal to x squared. That puts everything in the numerator. Nothing's in the denominator. And we can now use some online solver tool to solve and find out that x is 0.207. I'm not going to go through and show you solver. We discussed it the other day in the sense that there's online technologies, Wolfram Alpha and the like. Some calculators have solver functionality, but you're going to plug it into solver and you're going to get 0.207. And then again, if I go back and look at the ICE table, X happens to be the hydrogen ion concentration. So the question that was asked in the chat is, would we have to use the solver on the midterm? And the answer is, oh yeah. I don't care what expression you have. Plugging it into solver is probably faster than doing the calculation by hand. So even if it is something that is as simple as this expression right here, where'd it go? There it is. If you were to take this and plug it into solver as is, you'd probably be able to get the answer faster than if you were to do it by hand. So there's nothing stopping you from using solver on even ones that you can solve by hand. If you wish to use the quadratic equation, yes, I'm just trying to say that that's not going to work for a third or higher order polynomial, and it will actually take you longer to use the quadratic equation than it is to rearrange the expression into this form and plug it into a solver function. With regards to this expression, 0.207 also happens to be the hydrogen ion concentration. And so the pH is 0.68. And further on to Benjamin's question or point, I'm not going to limit the examples I give you to quadratics. There's so many more interesting questions and problems, real world problems, that are not quadratics, and you have the tools to solve them. So the simple point is, solve them. We're going to look at them. The next example we're going to look at is that of methylamine, Ch3nh2. This compound is a base, and it hydrolyzes in water to give the methylammonium ion plus hydroxide. I'm going to set up an ice table just to secure that space. We have 0.35 moles per liter of that, and 0 and 0 of this. And we'll get a Kb value in just a few seconds, but minus x, x, and x. There we go. In the context of this problem, in order to calculate Kb, we need to look for the corresponding or conjugate acid. And the Ka for the methylammonium ion is actually on the data sheet. And the Ka is 2.4 times 10 to the minus 11 moles per liter. We have the relationship Ka times Kb is equal to Kw. So Kb is Kw over Ka, which is, just to put everything in here, is that. And we get a Kb value of 4.2 times 10 to the minus 4 moles per liter. That is our value of Kb for this problem. I'm just going to go up here and substitute that in just to say Kb 4.2 times 10 to the minus 4 moles per liter. So now we can go through and solve this. And what we get is that 4.2 times 10 to the minus 4 is equal to x squared over 0.35 minus x. This is 10 to the minus 4, which is our threshold. We're right on the edge of this being extreme and not. So let's just hope for the best, and we're going to assume that x is negligible, and that makes this equal to x squared over 0.35. When you make that assumption, you find that x is equal to 1.21 times 10 to the minus 2. So to check, we have x over a is 1.21 times 10 to the minus 2. All that's divided by 0.35. And that is 0.034, which is just barely smaller than 0.05, but it's enough to say that this is valid. And I'm just going to finish off this problem in the last minute of class. Now if I go back to my ice table, and this is important, it's important to realize, the tablet catches up to me, that x is actually hydroxide. So in this example, x is equal to the hydroxide ion concentration, which was 1.21 times 10 to the minus 2 moles per liter. And there's a lot of ways to get to the pH. You could calculate the hydrogen ion concentration equals some number, and then calculate the pH. That's using the relationship H plus OH minus. Or you could sit there and go, the POH is equal to 1.92, and the same relationship applies. I'm just going to write down pH is equal to 12.08, which is the correct answer. And the relationship that we have here is pH plus POH equals 14. Or now over here, it's H plus OH minus equals 10 to the minus 14. In any case, the answer is 12.08. And there we have it. There's several more to do, but we will finish off this on Friday. I'm going to answer any questions that you have right now, but thank you very much for your patience, and we will see everybody on Friday. Are there any questions? Nope. Thank you. Well, you're welcome. I hope this is more than clear as mud. Thanks, Benjamin. Oh, he's already left the session.
Can I ask a question about the Hayden McNeil lab?
Sure.
The present one.
Go ahead, Jennifer.
Yeah, my lab 2, the screen looks oddly different from the other screens. I handed it in at the right time. There's no mark